Gosh, you. Hello.
You hear me okay?
Yep.
Excellent. How's your week been?
Been busy. How's yours?
Same, really, really busy.
Yep. I can imagine.
Yep, so today is our very last class of our season. It's a 2-hour class. So I want to start the same way we start all the other classes, seeing if you had any questions about anything at all, anything from my class, anything from your other calc class you're taking.
Yes, on the way you write integrals. So I did definite integrals last homework assignment, and I had these questions where I ended up getting confused, and I don't know. So like when we write an integral, you have the symbol, and then you have your limits of integration. Is B on top and A on bottom,
Yes.
and that's how it always will be.
Yep, in the basic case, yes. And then you have the function we're integrating. Sometimes we call this the integrand. So if you ever see this word being used in your textbook, they're just talking about the function that's integrating. So in this case, f of x would be the integrand. And then dx is the differential. Do you remember where the differential comes from?
No, I thought that was just something we put there all the time.
Well, for math, there's always a really good reason why we put things the places where we put them. This is a very important part. So remember the fundamental theorem of calculus, specifically part 1 of the fundamental theorem. It's the thing that establishes that derivatives and integrals are opposites of one another. Remember that we have something like this. So let's say we have dy dx, and we're trying to find the function that has this derivative. So the fundamental theorem of calculus tells us that whenever we integrate a derivative or differentiate an integral, they cancel out because they are opposites of each other, in the same way that adding and subtracting are, and logarithms and exponentials. So before we can even do that, we're going to have to multiply both sides by dx, because ultimately here, you know what, I think I'm going to use a different notation here. I like f of x better for this. So our goal is to find y. So we know how to get rid of the dx. It's a fraction. We always multiply both sides of the denominator we're trying to get rid of. So we have f of x dx. We no longer have a dx on the left side. But then our final step is to make this turn it into a y. We have a dy. What we really want to have is a y. So the way we do that is tricky. We have to integrate. So integrating is what turns a dy into just a y. And then, of course, we have to integrate the other side, just like we do with all algebra operations. So then the integral of dy is just going to be plain old y. So we have y is equal to f of x dx. So that's why we have to put a differential. That's just part of the original differential equation we had at the very beginning. It just comes from the differential equation. Makes sense?
Yep.
And do you remember what the difference is between a dx and a delta x? They're pretty similar, but they are different in some ways. Do you remember how they are different?
Well, delta x is change in x, so that would have to do with like a graph. Dx is just a part of dy over dx.
Well, they both represent a change in x. Delta x is a tangible change. Delta x can be measured. Dx, though, is an infinitesimally small. I don't even think I'm saying that word right, but you know what I'm trying to say. It's basically taking this towards 0. And then dx is the point where we get as close as we can possibly get to 0. So it's kind of like what we were doing with derivatives. Remember how when we were learning the limit definition of the derivative, first we had a secant line connecting 2 different points. And then we took the distance between those 2 points, because right now we have delta x. So we took the limit as delta x approaches 0 when we first started learning derivatives. And then it's easy to see why that is. So we're just going to bring points closer and closer together. So our new delta x is actually going to be a lot smaller than the first one that I picked on the graph. And the closer we get, the more accurate we get to the actual slope. So ideally, if we were to reach 0, that would be the derivative. That would be the tangent line as opposed to the secant line. So delta x is something that can be measured. This is a delta x. This is a delta x. But when they get close to overlapping, that's when it turns into a dx instead of a delta x. We're getting infinitely close to the point. And the same thing applies to integrals.
Yeah.
We're talking about the number of rectangles in a Riemann sum reaching infinity. So let's go over the notation for integrals and the rigorous definition first. Remember that we have a rigorous definition for integrals in the same way that we have a rigorous limit definition for derivatives. So remember where this all came from. It came from a Riemann sum. It came from the fact that we are trying to approximate an area under the curve. And we have my really ugly rectangles. And you can see that it is not a very good approximation at all. We have a lot of unused space that's going unchecked. We have a large margin of error. And do you remember what the ideal number of rectangles is to have the actual area with 0 margin of error?
There is no such thing because there will always be a margin. So the more you have, the better, the more accurate you get.
Yeah, but do you remember there is a very specific condition that, I mean, theoretically, we can't, I mean, hypothetically, we can reach it, but if we're drawing rectangles, we couldn't reach it. So hypothetically, there is a way to get 100% on this without any margin of error. Do you remember the process to get the perfect area without any error? There is a strategic way to do that. And I'm glad to hear that you're interested in taking Calc 2. Everything we do in Calc 2 is going to be based on this idea. It's going to be based on the concept of the integral. So the integral is probably what I consider to be the third main topic of the class. The first being limits, the second being derivatives. Third, of course, would be integrals. And then our fourth topic would be infinite series, which definitely build on integration a lot. So we really need to understand integrals really well before we can do infinite series. So back to this problem. Remember that there is a way to get the perfect area without any error whatsoever. It involves a limit, as it always does. The limit is the tool that allows us to go, whoa. The limit is the tool that allows us to go from an approximation to an actual correct answer. So let's rigorously define the definite integral. And I'm going to be lazy. I'm just going to use the thing I already have here. We rigorously define the integral as being the limit as delta x approaches, no, sorry, not delta x, limit as n approaches infinity of the Riemann sum. We're going to do I equals 1 to n f of c sub I times, no, sorry, not delta x, not dx, but delta x. So it's a big, scary looking thing. Let's take it bit by bit and see if we can break it down and see what each part really means in terms of the whole, in terms of the problem. So in this case, n would be the number of rectangles. So when we're taking the limit as n approaches infinity, right now we have only 6 rectangles. If we have 12 rectangles, it would be a little bit better. If we have 24, it would be even better. We're taking the number of rectangles to infinity. Theoretically, we're going to have an infinite number of super, super skinny rectangles. So that's what the limit as n approaches infinity represents. We're just taking the number of rectangles to infinity and beyond.
But doesn't that just equal infinity then?
Not necessarily. So if we had a function, if we didn't have a curve right here, if we allowed the rectangles to reach infinity without bound, then yeah, that would be infinity. But as it turned out, we do have an upper bound. So this doesn't actually reach infinity. It has a fixed value. But there's also another condition in which we would have an infinite value. If we had something like this, we're going to learn something called an improper integral later on, maybe in a few weeks or a month. An improper integral allows us to integrate things from indeterminate points. So for example, we could go from infinity to infinity. We could go 0 to infinity. And in this case, we would have an infinite area. But when we have fixed endpoints, we also have a fixed area. So if we're integrating from A to B, this is a fixed area. So we're taking the limit as the number of rectangles approaches infinity. And then we're taking the Riemann sum. Remember what this capital Greek letter sigma means? It means we're just adding a bunch of things together. We're taking the number, we're starting from 1 rectangle to n rectangles. So n would eventually reach infinity. But then let's talk about the things we're adding. So the notation tells us that for a sum, we're just adding all of this together at every step. And I forgot, have you done any coding before?
No,
No coding whatsoever? No understanding of how computer science and programming works?
I have an understanding, but I've never actually practiced coding.
Have you heard of a concept called a loop?
No.
So this is kind of similar to a loop. A loop in computer science is something that repeats an operation. So let's say we have a variable, and I promise we're not going to get too into it, but I think this is an interesting parallel. So we have an index. Let's say we start with I equals 0. Let's say we want to continue as long as I is less than, I don't know, anything less than 10. And let's say we want to increase I after every iteration. So then let's say we want to, this is going to be just a data abstraction. Let's say we wanted to print our index, print I. So the way the computer would interpret this, it would say, okay, I is 0. Print I, so it would print 0. And then it would print, it would increase I. So sorry, this is kind of confusing for you probably. I++ means it's just going to be increasing by 1. So the computer does this command, it reaches the bottom, goes back up, and now I is 1. It prints 1, it increases by 1, so now I is 2, goes down and comes back up. And sorry, this might be a confusing example, but it's kind of similar to what's going on here. We're going to keep doing this thing over and over and over again until we reach the end value we want. So let's talk about what f of c sub I is, and let's talk about what delta x is. So I'm going to pick a generic rectangle. I think I'm just going to pick this one right here. How do we find the area of this black rectangle? How do we find the area of any rectangle?
Maybe you could, since it's on a graph, you could use the graph to try to help you determine where it starts and where it ends, and gather its dimensions that way, and then use those dimensions for the area.
Right, exactly. So just in general, area is going to be base times height. So in this case, we have a base of delta x. And we have a height. What is our height of the rectangle? So notice how it depends on the function itself. So for example, this rectangle right here is going to be shorter than the first one I drew. But why is that? How do we know how high to make the rectangle?
Based off of which point on the graph it hits first, the top left corner of it.
Excellent.
Vertices.
It is the minimum function height. So this is our function height right here. So if we pick just a generic point, let's pick this point to be c sub I. So if this point is c sub I, then this right here would be f of c sub I. The point would be c sub I comma f of c sub I.
Mm-hmm.
So we're doing delta x times f of c sub I. This is just the area of one rectangle. So that's all this really big, scary looking thing is saying. We're just adding together the area of infinite rectangles. They're getting smaller and smaller and smaller. And the more we have, the more accurate the area is. So that's how we rigorously define the definite integral. And it's always something to fall back on. There are some things that can't be integrated due to the intricacies of the function itself. But we always have something to fall back on, kind of like how we have the limit definition of the derivative. So this is something that can always be used for a definite integral. It can't find us an antiderivative. This can only be used for a definite integral. We can't use it for something like this involving a plus c. It's only for definite integrals. So that's the skinny on how to derive the integral process. That's where this comes from. So now let's talk about how to actually compute integrals. I'm picky about the way things look.
Oh, you did give me a question to do, by the way, but I couldn't figure it out.
Oh, which one was it?
It was to calculate the integral of, I believe I think it was, I'm gonna write it down on the
Go for it.
I'm also once again on my laptop, so my handwriting isn't gonna be as nice.
So
Okay,
integrals.
so that was,
Mhm.
no, I was just saying that was it. Sorry.
All right, no problem. So integrals are hard. What makes integrals harder than derivatives? It's because derivatives are mechanical. You can take the derivative of anything. It's just a series of steps. It's an algorithm. Everything has a derivative, but integrals are much harder. People say derivatives are mechanical, but taking an integral is an art. Integration is an art. So we have to be really strategic in the way we tackle this. So what tools do we have up to this point? What tools have we learned to help us find integrals?
U sub.
That's a big one.
Uh,
That's probably the biggest one we learn in this class.
the anti-differentiation power rule.
Yep, perfect.
I would say that's pretty much all you need, considering everything else is sort of, I would say, more mental.
Mm-hmm. So let's have you practice an integral. So we want to find the indefinite integral of x cubed plus sine of x plus e to the x minus 1 over x times our differential dx. How do we want to start integrating this thing?
Well, okay, well, that brings into another rule.
Excuse
There's
me for 1 second, sorry.
Yeah.
I apologize about that. That was one of my other students. Oh, and they're calling me.
No, you're good.
Really, really sorry about that. That was really unprofessional, and I apologize.
No, you're good. That's all right. Actually, I'm actually kind of curious. I thought you were home. Are you at like Root STEM Academy right now?
Well, I do root stem from home.
Mm-hmm.
I do everything from home, basically. My root stem classes and my private tutoring, it's all from home. At one point, I had a physical classroom, and I really miss it. I miss my classroom a lot, but right now we're forced to work from home due to COVID.
Mm-hmm.
And I'm actually moving to
Reno.
Okay. I'm moving back to Reno next month, so I'm not going to be, I don't think I'll ever be back in my old classroom.
Wow, are you going back for your classes? Are you taking classes at UNR?
Yep, going back to school.
Okay, well, I wish you the best of luck for that when the time comes.
Thanks a lot. I appreciate that. And I'm still going to be doing everything I normally do. I'm just going to be continuing root stem and my private tutoring from Zoom. So I'll be able to do that remotely with the same level of quality.
Yep, okay.
Okie dokie. So we have a problem. How do we integrate this thing?
Well, this brought me to another rule, which is the sum rule for integrals, where it's pretty much the derivative rule, but you can do it with integrals. So you can take the integral of each term separately and then add them all together, and that's how we get the original function.
Exactly. So let's just integrate everything term by term. So how do we integrate x cubed?
This one, there's a rule for it, but this one's pretty easy. So you would have to think like what do you have to derive to get x to the 3? So you have to add 1 to the exponent, and then 4, you're going to need something that multiplies by 4 to get you 1. So that's going to be 4's reciprocal. So it's going to be 1/4 times x to the 4th.
Wonderful. All right, and then what about the next part of this? How do we integrate sine of x?
Sine of X, I'm pretty sure this is a U sub question or a U sub thing, but I typically just do this subconsciously.
So there's something we can use to help us. So we know when we take the derivative of sine of x, we get cosine of x. Now, what is the derivative of cosine of x?
The derivative of cosine of X is negative sine of X.
Wonderful. And then the derivative of negative sine of x is negative cosine of x. And then the derivative of negative cosine of x is negative sine of x. So just positive sine of x. So whenever we move down, we take the derivative.
Yeah.
Whenever we move up, we take the integral. So we're trying to integrate sine of x. So we have that right here. The integral of sine of x would just be a negative cosine of x. That is our antiderivative. All right, now let's go ahead and take the antiderivative of e to the x. Do you remember what that is?
Yes. E to the x is one of the only functions that has itself for the anti and for the integral and for the derivative. So in this case, since it's also just e to the x, it's just going to be e to the x.
Wonderful. And then what about negative 1 over x?
This one, first I would start by moving the negative outside of the integral, and then you can see that you have 1 over x, so you'll know that, well, I mean, if you look at the rule, you'll know that it's natural log of x.
Wonderful.
My negative natural log of x.
Are we done?
Yes.
We're missing one thing.
Oh, plus we need a plus c because this wasn't a definite integral.
Perfect. We are finished. All right, so you have a pretty good understanding of how antiderivatives work. Antiderivatives are the most versatile tool we have at our disposal for finding integrals. So let's maybe work on some more involved integrals. So there are going to be some times when we're given really complicated trig integrals, and we want to know what to do in situations like those. So for example, what if we had cosine cubed of x dx, and we're trying to integrate this function? How do we integrate something like this? It would be a lot easier if we had a sine of, and maybe a negative sine of x in there somewhere. If we had this, it would be easier if we had this because we have a u sub problem now. This would be our u, this would be our du. We would have u squared. That would turn into 1/4 u to the 4th power du, and we're finished. But unfortunately, we don't have a sign to help us with the u sub process. So we have to do something else. U sub won't really help us, at least not at this point. So do you have any ideas on what we can do for this?
We could try to rewrite cosine of x as cosine x times cosine x times cosine x.
That's a great place to start. And the screen is going to get it's probably going to look weird for a second. I need to pull up my Trig Identity sheet real quick.
Yeah, it's been changing around.
So the theme of this chapter in the book aims to, the theme is using trig identities to help us rewrite something so that we do know how to integrate it. So do you know any trig identities that might be useful in this situation? So I think we might be able to turn this into a u sub problem using the trig identities. How do we accomplish that though?
Well, we could rewrite it as cosine squared x times cosine x, and then we could replace cosine squared x with 1 minus sine squared x. That's it.
I want to see if you can take it from here.
Okay. I'm going to do it on my paper.
Sounds great. And while you're working on that, I'll be right back and I'll let you know when I come back, okay?
Okay.
All right, and I am back. I apologize for that. You might be on break too. Oh, all right. No problem. How's the problem coming along?
So far, I can't tell. I think I rearranged it to where we can make a use of.
Perfect. That's the goal. What'd you do?
I changed cosine cubed x to dx to cosine squared x times cosine x times dx, and then changed cosine squared x to 1 minus sine squared x times cosine x.
All right.
Then I expanded. So you have cosine x minus sine squared x cosine x. And I expanded sine squared x to just be sine x times sine x. After that, I chose u to be cosine x, and then du would come out to be negative sine x dx, which I then replaced in the right side of the integral of the whole after the negative, after the minus sign. So basically, I had the integral of u plus u du sine x.
Okay, so what did you get for your answer?
I got in total overall I got sine x times in parentheses 1 minus cosine squared x.
Is that all?
Plus e.
Yep, there we go. So let's see if I get the same thing. So I'm going to use a similar strategy to what you did. I'm going to distribute. So I'm going to distribute the cosine of x to the 1. So we're going to get just a single cosine of x. And you don't have to do this, but whenever I'm doing a problem like this that involves u sub, I always break it up into multiple integrals just so we don't get the definitions of u and du confused. It's less to worry about if we have multiple integrals. So when we distribute the cosine x to the 1, we just get cosine of x dx, and then we're going to have a minus another integral. We're going to have minus the integral of what we get when we distribute cosine to our second term. We're going to have sine squared x times cosine of x dx. And then our first one is really, really easy to integrate. We remember that the antiderivative of cosine is just going to be sine. So we have sine of x for our first antiderivative. And then after that, we have to integrate this one using u sub. How do we know if we're able to use u sub or not? What's the criteria?
One term in the function has to be the derivative of another term in the function.
Right, exactly. So does it matter which one we pick? Could we pick u to be sine or u to be cosine? Does it matter?
Yes.
It absolutely does. So we can have a u squared. That's perfectly okay. But what we can't have is a du squared. And I recommend you put this in your notes. It's not okay to have a du squared. We can only have a u squared. So that being said, if we pick u to be cosine of x, theoretically, du would be minus sine of x. And we can't have that because this would be, well, we have minus sine of x right here. So that would be du squared times u. And we can't have a du squared, which means this substitution is not the one we want to use.
Du squared from that.
Sorry?
How would you get du squared from that?
So we have du right here. Our definition of du is negative sine of x.
Oh.
So we square both sides and we would get this.
Mhm.
And we can't have a du squared, so that's why it's not a very good choice for a substitution. That being said, I'm going to make u be cosine, or make u be sine of x instead of cosine. All right, so we have our u, we have our du. So we're going to subtract. Oh, I forgot the dx, the differential. Yep, so this right here is du. This right here is u to the second.
Mhm.
And then from there, all we need to do is apply that integration power rule. We're going to add 1 to the exponent and then divide by that result. So we're going to get sine of x minus 1/3 u to the third power. So it's going to be 1/3 sine of x to the third power plus c. And this right here is our answer. It's kind of tricky. So let's try some more of these. Is it all right if I erase this?
1 second, please.
No problem. Take your time.
Okay.
Next up, we have the integral of sine to the 5th power of x times cosine to the 2nd power of x dx. And we want to know how to integrate this thing. Do we have any ideas on how to rewrite this thing so that we can integrate it? We have to use trig identities again, but which ones do you think?
Probably some iteration of the sine squared x plus cosine squared x is equal to 1.
Absolutely. So we want to pay careful attention to the powers and the parity of those powers. So parity of a number is whether it's even or odd. So the parity of our sine of x is going to be odd. The parity of our cosine of x is going to be even. So we want to take that information into account when we make our decision on how to rewrite this. So let's think about the best way to approach this. Ideally, we want to set it up to be a u sub problem again. We want to have a u and a du. So we're going to need, remember that we can't have a du be any power. We can't have a du squared. We can't have a du cubed. We can only have a du to the 1st power. So that means we're going to need to break this up in such a way where either we have just one single power of sine or one single power of cosine. That is our goal. How do we do that? How do we do a reduction of powers to just a single power to either sine or cosine? Any ideas? The thing you mentioned earlier plays a really, really big part in helping us get there.
Oh, well, in that case, I would probably just, first step, I would rewrite it as like sine squared x times sine squared x times sine x. And then I'm pretty sure you could already just replace cosine squared x with 1 minus sine squared x.
Yep. 1 minus cosine squared x. So we're going to replace this one with 1 minus sine squared x, and same thing with this one right here. No, sorry, I meant to say cosine of x. We're going to replace both of them with 1 minus cosine squared x.
Okay.
What do we want to do after this step right here?
Well, we have a sine x and a cosine squared x, so we can
I think we're going to need to expand this. We're going to need to multiply these together and then by that. So we're going to get sine of x. And this is a lot of writing. I think I'm going to just maybe type it instead.
Okay.
So we're going to get 1 minus 2 cosine squared x. And I'll put the exponent in a little bit later. And then that would be plus cosine to the 4th power of x. So we have all of that times cosine squared x. So the next thing we want to do is we want to distribute. We want to distribute the sine of x to all 3 of our terms on the inside of the parentheses, and we also want to distribute the cosine squared x to all 3 of the terms. So let's see what that part would look like.
How would you know that that's what you wanted to do? Like when you look at this problem, what do you think first when you see this problem? What do you think is like what goes on in your brain that tells you what the first step is?
Great question. So when I see something like this, I mean, I've done these enough times where I know we have to have just a single power. Either we need to have a sine of x to the 1st power, and cosine of x could be anything. So if we have a single power of sine of x, cosine could be any power at all. Or what we could do is we could have a single power of cosine. And the reason why I know that is because we can't have a du squared. We can only, in the u substitution situation, we can only have a u to some power and then a du to the 1st power. So right away, I'm thinking about a way where I can reduce one of these powers to a single power. And then the way I figure out if it's going to be the sine or the cosine is because cosine, it's not really easy to work with when we have a 2nd power like this. So theoretically, what if we wrote it like this? What if we wrote it as cosine of x times cosine of x? Well, we do have one single power of cosine of x. That part checks out. But then what are we supposed to do with this right here? We can't do anything with this other cosine of x because the Pythagorean identity only applies when we have a cosine squared x. So if it were cosine squared x, we could rewrite it in terms of sine. But as a single power of cosine, we can't do anything at all with this right here. So that's what kind of tipped me off and told me that we have to do a reduction of powers with the sine. So it's always going to be the odd power that you want to reduce, not the even. An even power doesn't play very nicely. So whenever you see a problem like this with multiple trig functions, one odd and one even, you always want to reduce the odd power. And this is how we reduce that odd power.
Okay.
Great question. So now let's go ahead and distribute. So we're going to get sine of x minus 2 sine of x. This is going to be 2 sine of x cosine squared x. And then we're going to have plus sine of x cosine to the 4th power of x. And then we're going to distribute the cosine squared x as well. So this is going to be cosine squared x right here. Where'd the x go? Kind of need that x to be there. And we already had a cosine squared x right here. We're going to have 2 of those, so this is going to become cosine to the 4th power of x. And then this one at the end is going to turn it into cosine to the 6th power of x. All right, so far so good. Let's think about what we want to do next. What kind of a strategy do you think would be useful to do this next part?
Separating each integral.
Mm-hmm.
I mean, separating the whole integral into 3 smaller ones.
Perfect. What I'm going to move this 2 out front in the second integral. And then we're going to have plus another integral. So now we have a u sub situation for all three. What do we want to be u and what do we want to be du?
I would say let me think here.
No problem. Take your time. It's always a really good idea to be strategic in how to do this.
I'm going to say cosine of x should be u.
Yep, you're absolutely right.
Okay.
So then du is negative sine of x. dx. So let's see if you can carry this out to the end now that we have a u and a du.
Okay.
So the first one, I'll help you rewrite the first one. This is going to be a u squared. And because we don't have a negative sign, I'm going to make this, instead of du is negative sine of x, I'm going to make this into a negative du equals positive sine of x. So that tells us that we need to put a negative sign on the outside of the integral. So that's the first one. See if you can carry on from here. Let me know when you have an answer and let me know when you need some help. Let's go through this together. So we have our first integral is going to be this. Second integral, we have a negative sign already there. We're going to apply this negative sign from the du. We're going to have a negative and another negative. It's going to turn into a plus 2 times the integral of, this is going to be u to the 4th power du. And then after that, we're going to have another minus sign because we have a minus from the du. It's going to turn into a minus integral. And then this is going to be a u to the 6th power times du. And then from there, we can apply the integration power rule for all three of our terms. So this is going to be negative u to the 3rd power over 3. And this is going to be plus 2 times u to the 5th power over 5. And then we're going to have minus 1/7 u to the 7th power. And then plus c. So that's what this turns into. Any questions?
No. Basically, what I did is I just put everything under a common denominator.
Oh, I see. I see what happened. That makes.
Should I not do that?
Yeah, that won't be necessary.
Okay.
All right. Let's do some more. Let's try something trickier. Let's try a single even power of sine of x to the 4th. So do we have any suggestions on what we want to do here? I'll give you a hint. We're not going to be using any of the identities we've used so far today.
We're not gonna. Could you repeat that?
So we're not going to be using any of the identities we've used so far today. We're going to use something a little bit different.
Okay.
So do you have any suggestions on how we can rewrite this so that it can be integrated?
I mean, we could try sine of x times itself 4 times.
Yeah, take a few minutes and see if you can find any ideas, any strategies that we can use in this situation.
Okay.
So a really good a trig identity we want to use in a situation like this one might be one of the half angle or double angle formulas. And the reason why those are a good idea is because we can see that we have something in the second power going to something in the first power. So I want to write down what I'm talking about so far. So this is one of the half angle formulas. We have sine squared x equals 1/2 1 minus cosine of 2x. So if we have this by itself, it's not easy to integrate because of that double power. But if we have something like this, we can integrate this pretty easily using u sub. So it's always in our best interest to break something down from a second power into a first power whenever possible. So I want to maybe rewrite this as sine squared x to the second. And then from there, we can go ahead and rewrite it like this. We're going to make the inside of the parentheses this expression. And I'm going to distribute. We're going to have 1/2 minus 1/2 cosine of 2x. Actually, you know what? For now, here, I think I want to square this first. So if we square this thing right here, what we get is 1/4. And then we have 1 minus 2 cosine of 2x minus cosine squared of 2x, no, plus cosine squared of 2x. And we can move the 1/4 to the outside of the integral. So we're going to have 1/4, 1 minus 2 times cosine of 2x plus cosine squared of 2x dx. And then this part right here is a little tricky, the cosine squared of 2x. I want to see if you can integrate up to this point. And feel free to try this one if you want, but I want you to at least integrate the first 2 parts of this.
The antiderivative of any constant is just 0, right?
The derivative is 0, but the antiderivative of a constant would be a single variable. In this case, it would be x.
Oh, right, my bad. Antiderivative of 1 and of cosine 2x.
How do you integrate cosine of 2x?
Well, it starts out as so it starts out as -2 cosine 2x, but when you split it up, you take out the -2. So I have 1/4 times, in parentheses, the integral of 1 dx minus 2 integral of cosine 2x dx plus the integral of cosine squared 2x dx. And then
but don't forget to distribute the 1/4 to all three of the integrals. They all have to have 1/4.
yeah, so I was gonna try and do that after I integrated all three of them, but I said just do that right. So it'll just be x over 4 and then minus cosine 2x over 4.
All right, and then how do we integrate cosine of 2x?
The argument in, so this one you'd have to do the I guess you'd have to do u sub for, or the chain rule for anti-differentiation.
We have to.
I don't know. I didn't really do that. I just thought it to my mind, because when you take the derivative of sine, cosine, or tangent, it's just that. But then you have to do the chain rule of the argument for the argument. So the derivative of 2x is just 2. So since our coefficient was 1, and then you're going to end up getting a times 2. You obviously have like a 1/2 somewhere in there. So once you integrate cosine of 2x, you have 1/2 cosine 2x, and then times -2 is just negative cosine 2x.
All right. So u is 2x, 1/2 du is dx. So we're going to have another 1/2. This is going to be minus 2 over 4 times 1/2 integral cosine of u du. And when we integrate cosine of u, we just get sine of u. So the 2 on top will cancel with the 2 on the bottom. We get minus 1/4 sine of u.
For the u and then the 1/2 of du that you wrote, where'd you get the 1/2 du?
So what I did is I took the derivative of this. So u is 2x, and then we have the derivative of u with respect to x. So that would be du dx is equal to 2. Derivative of 2x is 2. So then I multiply both sides by dx. And I divided both sides by 2. So we get 1/2 du equal to dx. We just manipulated the differential equation.
Why do you choose to get 1/2 du?
I mean, it's just the way I was taught to do it. It just kind of makes sense to me. I mean, technically, you probably don't even have to, because you have a 2 and a dx right there. But it's just a really clear way to keep track of everything you have. I found out that if I try to do it the other way, I end up having an extra constant, or maybe I don't have the constant I need. This is just a way to make sure, 100% sure, that I don't have any constants that I don't need and I'm not missing anything. So just to make sure I have everything where it needs to go, this is the process I use. So this is going to be 1/2 du. So we get minus 1/4. It's going to be sine of u. And then the u is just 2x. Put that back in there. And then we're going to do another power reduction here. If it were just a single power of cosine, we could do this pretty easily. But the problem is we have a double power. So we're going to use another power reduction formula here. I'm going to do some spring cleaning real quick. Let's take a look and then see what might be useful from that identity sheet. Which one do we want to use? So I'm thinking we probably want to do the one that goes like this. We have cosine squared x equals 1/2 1 plus cosine of 2x. So let's go ahead and use this one. So this is going to turn into, how does that work when we have an argument of 2x? I think it should still work the same way. Yep, it will. Perfect. So I want to modify this to account for the fact that we have a cosine of 2x, cosine squared 2x, and not just a cosine squared of x. So I'm going to modify this identity. I'm going to make some modification to it real quick. I'm going to go from having an x to having a 2x. And that's also going to affect the right side. We're going to have 1/2 1 plus cosine, not of 2x, but it's going to turn into a 4x. All right, there we go. So we already have the 1/4 there. What we don't have is the 1/2. So we're going to have 1/4 times 1/2 integral, and then this is going to be 1 plus cosine of 4x. And then we're going to have this coefficient be 1/8. And then we're going to make this into an integral of just 1. That turns into x. And then I'm going to make another integral. I'm going to distribute the 1/8 to the other integral, cosine of 4x dx. So then we're almost done. We have to do another u sub. So u is equal to 4x. du is going to be 4 times dx. And then I'm going to modify this the same way I did in the last u sub. I'm going to make this 1/4 du equals dx. So I'm going to multiply the 1/8 that's already there by 1/4. And then this is going to turn into cosine of u. And then the antiderivative of cosine of u is just going to be sine of u. So we're going to have sine of u. So that is sine of 4x. And then I'm going to combine these into 1/32. So we're going to have 1/32 sine of 4x. In addition to everything else we already have. Let's see if I can do this. Oh, and I forgot the 1/4 x. Well, that was really, really tricky, but we got there in the end. It's good to have practice with this kind of thing. Any questions?
No. So wait a minute. For the second term, how'd you get sine of 2x?
So I did a u sub. So I started right here. So I did a u sub. I set u equal to 2x, and then I took the antiderivative of cosine of 2x, which would be sine of 2x. So that the cosine of 2x turned into sine of 2x.
Oh, okay.
All right, let me know when you are ready to continue.
Is there a plus in between 1/8 x and 1/32 sine 4x?
Yes, there is. Thank you for that.
All right, I'm good.
Let's try another. Let's try tangent to the 5th power of x times secant to the 7th power of x dx. So let's go ahead and see if we can manipulate this in such a way that we can integrate it using the rules we know how to use up to this point. So it's a little bit different from the other two. We're going to have maybe different identities to use for this one. So we're going to use identities, but not only that, but we want to examine the relationship between tangent and secant as far as derivatives are concerned. So when I was first learning this, I was always in the habit of putting the derivatives off to the side. Always to just have a quick reference if I should need it for anything. So the derivative of tangent of x is secant squared of x. Secant squared of x. And then do you remember what the derivative of secant is?
It's self times tan x.
Yep. Perfect. So we want to think about a way to write this. It's going to be a u sub problem. We want to see what should be u and what should be du. So whatever happens to be du, we want to have a single power. So we're going to need one single power and then one other power that could be any power whatsoever. So let's think about a good way to approach this one. Oh, and then I also want to write the Pythagorean identity. So let's think about this. We could try manipulating this and making one of the terms secant and tangent. So let's see if we can factor out a secant of x and a tangent of x from everything. If we take out a tangent, we're going to have a tangent to the 4th power. If we take out a secant, we're going to have a secant to the 6th power. Then we're going to have a secant of x times a tangent of x.
Then u would be secant 6x, or u would be just secant of x, and then du would be tan x secant x dx.
In a perfect world, yes, but we still have this tangent to the 4th power to worry about. We're going to have to do something with that in order before we can even do that step. So we're going to want to put tangent in terms of secant, and that's easily done. So I want to manipulate this equation right here. I'm going to subtract 1 from both sides. And we get this. And then because we have a tangent to the 4th power, not a tangent squared, I'm going to square both sides of this equation. So we get this. Tangent to the 4th power of x is going to be secant to the 4th power of x minus 2 secant squared x plus 1. So now let's go ahead and replace this with what we just found. Here on Untitled.
Did you expand secant squared x minus 1, everything squared?
Sorry, what?
Well, what? No, actually, never mind. Nothing. I'm good.
All right. So we have secant to the fourth power of x time minus 2 times secant squared of x plus 1. That is equivalent to tangent to the fourth power of x. And then we have secant to the sixth power, and then secant of x times tangent of x. This works really, really well because if we look at what we have now, if we look at this part, we have everything in our u term in terms of just secant, which is really, really nice. So we can have secant be any power, we'll have our u to some power, and we'll have our du. Life is good. So I want to see if you can carry on from here. Do you feel prepared for this?
Yeah, I'm gonna try.
Give it a shot. Let me know if you need some help. What'd you do?
So from where we left off, that's where I decided u is going to be secant of x, and then du is equal to 10x secant x dx. So from there, I expanded secant 7x into secant 4x minus 2 secant squared x plus 1. And that gives you secant 11x minus 2 secant 9x plus secant 7x. And then the rest of the integral I replaced with du. So after that, I separated the integral into three separate ones, into three smaller ones. That one, the first one being secant 11x du, and then minus 2 integral of secant 9x du, and then plus the integral of secant 7x du. Then I replaced all the secant x's with u, so you have 11u du minus 2 integral of u to the 9, and then du plus integral of u to the 7 du. And so that pretty much comes out to be 1 over 12 u12 u to the 12 minus 1 over 5 u to the 10 plus 1 over 8 u to the 8 plus c. And then I just replaced u again with secant x for the final answer.
That's correct. You did very well.
Okay, nice.
Getting the hang of this.
Yeah, the more use of I practice, the better I'll have it down.
Yep, that's how it is. Let's try a secant cubed power. Try it, see if you can find the integral of secant cubed of x dx.
Oh, also, I was wondering, are there half angle identities for the inverse trig functions? So secant, cosecant, and cotangent?
No, there are not. Not for inverse trig. Oh, you mean, oh, you don't mean inverse. You mean the reciprocals, right? Like cosine is 1 over secant,
Yeah.
that kind of thing?
Yeah, the reciprocals.
It's not on the sheet, but here, let's take a look real quick. We might be able to derive it ourselves. So, for example, sine squared x is 1/2 times 1 minus cosine of 2x. So, for example, if we wanted to find cosecant squared, we would just have to take the reciprocal of this. Equals all of this stuff. So then cosecant squared would have to just be the reciprocal of everything that appears on the right. So it would be, let's see this. It would be 1 over all of this stuff. So yeah, it would be pretty nasty, pretty ugly, but yeah, theoretically you could. You just have to put you would have to put it in terms of its reciprocal. In this case, it would be in terms of sine. Make sense?
Okay. Will we be using that?
Nope, not in this class, and not in Calc 2 either.
Oh, well, that's good.
There are always much easier ways to get the answers than that. All right, what do we want to do in this one?
I'm just thinking over all the trig identities that I know.
Very good. Take your time.
Or try to get like some of them in terms of tan and then find a u and a du.
I think that's a great idea. So
Okay.
I want to see if you could rewrite this for us in a way that will allow us to integrate. So what is the first step we want to do here?
I'm thinking write it as secant squared x times secant of x, and then using that one identity. Give me a second. Okay, so secant squared x is equal to 1 plus tan squared x. How would that help us?
All right.
I think then we can yeah, after that I would expand.
So we could do it this way, but it would be really, really complicated. So for example, secant of x, it is possible to take the antiderivative, but it's hard. I'll show you how to do it if you want, but it's not the best way to do it. And then the same thing with our second integral. If we had a tangent to the first and a secant squared power, that's what we want. But it's really hard to have it the other way around.
Okay. If we have time, you could show me, but for now, I think we should find the easier or the more strategic route.
So actually, you know what? This relies on a topic called integration by parts that we'll be covering in Calc 2. But you know what? Actually, I want to give you kind of a preview of integration by parts. I would say that it's the second most useful integration tool we learn after U substitution. So let's just spend the last 15 minutes or so of class going over this new topic.
Okay.
Super highly useful subject, integration by parts. So u substitution, we can think of that as the inverse of the power rule, the inverse of the chain rule for derivatives. Integration by parts can be thought of as the inverse of the product rule for derivatives. So in general, the formula would go like this. It relies on two functions.
I'm going to have to go get my charger for my laptop. I'll be right back.
No problem. Oh, sorry, I forgot to hit the recording. So before integration by parts, there's no clear way to integrate this. U sub won't really work because if we said u to be cosine of x, du would be sine, and we don't have a sine anywhere. If we said u to be x, du would be 1, but then we don't have anything to do with the cosine. We can't do anything with that. So this is where integration by parts comes in. So whenever you see something like this, something times something else where u sub doesn't work, that's just kind of a dead giveaway that we have to do an integration by parts. Kind of like when you see an inner function and an outer function like this, you know that's a u sub. Whenever we have a setup like this, this is integration by parts. So we have to be really, really strategic in what function we pick to be u and what function we pick to be dv. So I highly recommend you write this down. So to pick u, we always want to pick the function that gets simpler when we take the derivative. And that's pretty big. I want to see if I can maybe just resize that. There we go. So we have two choices for u. If we look at this problem right here, we have an x and we have a cosine of x.
It's going to be x.
Exactly. Because when we take x, the derivative of x is 1, and the derivative of 1 is 0. Cosine, if we take the derivative of cosine, we get negative sine of x, and then we get negative cosine. So you can see that this doesn't break down. It just keeps repeating over and over again. Eventually we end up where we started. So u should always be the function that gets simpler. So u should be x this time. So u should be x. So I'm going to start labeling things. So I'm going to have this be u, and then automatically everything else is going to be dv in that case.
What is dv? Where does the v come from?
Sorry?
What is dv? Where does that come from?
Well, we have two functions in this case. We have a u and we have a v. So du is the derivative of a function u. dv is the derivative of a function v. So dv is just the derivative of v, and du is the derivative of u.
So how is cosine of x dv? Or can you just pick it whenever you know that you have this kind of problem?
So how do we know what should be u?
Well, u is the one that gets simpler when differentiated.
Absolutely. So in an integration by parts problem, we always start with this very first step. We always start by selecting a u and selecting a dv. So we already have our u. That means everything else is automatically going to be dv. So after you have u, you just have everything else be a dv.
Okay.
And it's one of those things where it'll make sense the more we practice it, kind of like with u sub.
So the dx is also a part of the dv, right?
Yep. The differential always contains the other differential.
Okay.
So we have a u, we have a dv. What we don't have is a v, and we don't have a du either. So let's go ahead and find those real quick. So u is equal to x. So I want to start by defining everything we have. U is x. Du is going to be, well, the derivative of x is just 1, so that's going to be dx. And then we find,
sine. Wouldn't v just be sine?
v would be sine. Yep, exactly. So u is x, du is dx, dv is cosine of x. dx, and then you are right. So v is going to be the antiderivative of cosine of x, so we get sine of x. So now that we have all of our definitions, we can start by substituting everything into the formula. So this integral is going to be equal to u times v for our first term. So we're going to do u, which is x, times v, which is sine of x. In the next part of this, here, let me label this. This is v. And then after that, we have minus the integral of v, which is sine of x. v times du. du is just dx. So let's take a moment and look at what we have here. Let's see if we're happy with how things are going so far. So we started with this right here. No idea how to integrate this. But what we've done is we've broken it up. So this part right here, there's no calculus whatsoever. This part's good to go. We don't have to integrate. We don't have to take any kind of a derivative. So this part has no calculus to do. And then this right here, this is super easy. We definitely know how to integrate this. So that's why integration by parts is such a useful tool. It breaks it up into two things that are easy to work with. So we're really good at this kind of thing by this point. So what I'm going to do is I'm going to move to the next line. This is going to be uv is x times sine of x. And then the antiderivative of cosine, the derivative of cosine is negative sine, which means the antiderivative of negative sine is going to be positive cosine. So when we integrate negative sine, we get positive cosine of x plus c. And we're finished. Now, I'd like for you to do me a favor. I'd like for you to take the derivative of this. If we call this f of x, I want you to find for us f prime of x and verify that we did this correctly.
Okay.
So we have taken the derivative and we have confirmed that we got exactly the answer that we are trying to get. So that's integration by parts in a nutshell. I want you to try a problem for me. What I'm going to do is I'm going to erase all of this. It's being recorded. And we have just one problem to do right now. I'm going to leave this formula up here. I want to see if you can integrate the natural log function for us. And this is something that we can't do without integration by parts. It doesn't even really look like an integration by parts problem because we don't have something times something else, but it definitely is. And you definitely have to be strategic about what should be u and what should be dv. So I want you to take a few minutes to give this a try and let me know if you have any questions, if you'd like some help.
All right.
Sorry, I had the recording off. So like I said, I'm really glad you've decided to take Calc 2 with me. When are you going to be able to start that? Are you able to start right away?
Yeah, pretty much. You just have to let us know how we'll pay you, and then yeah, we can just do the same thing really, or whatever works for you.
All right, perfect. So I think we'll maybe keep the same schedule. We'll do twice a week if that works for you, Tuesdays and Thursdays.
Yep.
And I will email your parents. Can you text me your parents' email so we can discuss this a little bit more later?
Yeah.
All right, excellent. So this is going to be our first Calc 2 topic. I want you to finish this problem for homework, and then we will be doing it together later on when we have class.
Okay, sounds good.
All right. If you have this copied down, you're free to go. Have a wonderful weekend, and I'll see you next week. See you in Calc 2.
Okay. All right. Sounds good. Thank you. Have a good day.
See you later.